Alright, let's go through the next part of this math handout here. So a lot of times in this class we're going to be solving simultaneous equations. And sometimes they'll be simple kind of linear equations like we see here, and sometimes it'll be something a little more complicated. But let's just think about a couple of ways to solve some linear equations. So taking this first set over on the left-hand side, what we would be imagining here is that we have perhaps a supply equation with the positive slope and a demand equation with the negative slope here, and we want to solve to see where these two lines intersect. So two equations and two unknowns, how are we going to solve these? Well, in this kind of case, it's pretty easy because we have P equals 2 plus 3Q, and we also have P equals 20 minus 2Q. So the simplest way I know of in this case is to set these two right-hand sides equal to each other because they're both equal to P. So we can just say, let's set 2 plus 3Q equal to 20 minus 2Q. We can just solve this equation for the equilibrium value of Q and then plug it back into either of these two equations and get the value for P. And how you go about doing the steps, I want you to do these things any way that you are comfortable with. As long as you're doing it a correct way, there are a lot of ways you can do this. But in this case, the way I would probably approach this is to take this plus 2Q and add it to both sides, and then take this 2 and subtract it from both sides. And that way we get all the Q's on the left and numerical values on the right. So minus 2Q plus 2Q on the right plus 2Q on the left. We get 5Q's on the left. And then equals, subtract 2 from both sides. We get 18. Divide both sides by 5. And looks like we have Q equals 18 over 5. Most of the time in this class, it's going to be a little more convenient to represent things as a decimal instead of as a fraction like 18 over 5. So go ahead and do 18 divided by 5 on your calculator. See what you get. Looks like we get 3.6. And then we take that 3.6 and plug it back into either one of these two equations, and that will give us P, whichever one seems easier. Looks like, I don't know, to me maybe the second one. It doesn't matter, but 3.6 times 2 I know is 7.2, and then we can just take 20 minus 7.2. Looks like that would give us 12.8 for the equilibrium price. Now, if you're ever unsure, you can plug it into both equations, and you have to get the same thing. So P equals 12.8. And I encourage you, instead of, when you solve for something that's a price, instead of calling it 12.8, think about this as being in monetary terms. This is a price, so it's in dollars or euros or something like that. So think about this as being $12.80. It just helps the answer be a little bit more real than being some abstract number. All right, let's think about this situation over on the right. We have Q equals 15 minus 2P, and 2Q equals P plus 20. There are a lot of ways we could go here. You think of something you could do to solve this. So a couple of options. We could take a similar kind of strategy we did last time, except here we have 2Q, and so we'd have to convert this equation into Q instead of 2Q. So we could just take this entire equation here and we could divide everything by 2 and end up with something like Q equals P over 2, or 1/2 P, right, plus 10. And then we would have both of these things, 15 minus 2P and P over 2 plus 10, are both equal to Q. And then we could set those equal to each other, solve for P, plug back in to get Q. That's one way we could do it. I'm going to try a different way here. One thing we could do here, and I'm not saying this is necessarily the easiest way, I'm just showing you a different way to approach this problem. We know that Q is equal to this part, so what we could do is take 15 minus 2p and we could plug that into this equation for Q. That's technically what we were doing over here. We were taking, say, this is P equals 2 plus 3Q, and what we're really doing is plugging that in there for P. That's what we're doing when we're setting those equations equal to each other, right? Except here we're plugging in 15 minus 2P here for Q, and so we're going to have to multiply that by 2. So if we took that route, and again, I want you to do things in whatever way makes the most sense for you, and I'll usually try to show you a couple of different ways to approach things. So let's do this method and see what we get. 2 times Q is equal to 15 minus 2P. And then set that equal to the P plus 20 there. All right, take a minute, pause the video, and see what you get for P. And then plug that back in and see what you get for Q. You're going to have to take the time in this class to solve these things for yourself. It's not a spectator sport. You can't get to where you're good at these things if you just watch me do it. So please pause the video, take a minute and do this. All right, so I would get 30 minus 4p equals p plus 20. And here I would subtract that 20 from both sides and end up with 10, 30 minus 20. And then I would add that minus 4p to both sides and get 5p on the right. Divide both sides by 5 and get p equals $2. And again, instead of just saying 2, make it real. Make it into something we are interpreting, because this is applied math. We're just not solving these equations for the sake of solving equations. Now we just take that 2 and plug it back into either equation, and probably this top equation here is going to be easier because we just plug in 2 here. 2 times 2 is 4. 15 minus 4 gives us the equilibrium quantity is going to be 11. So the equilibrium price is $2, and at that price, people are buying 11 units, assuming that's the context of what we're talking about here, is demand and supply. All right, let's review some exponent rules. So this is partially to try to see what's already in your brain here, see what you can recall, but we'll be stating what the general rule is we should be thinking at the time. And again, let's do this actively together. Let's start with this first equation here. What we want to do is try to simplify this if we can, and if we can't, just say that we can't. So here we have y squared times x cubed plus y cubed times x squared. Can we group those and simplify this in any way? And the answer is no, we can't. So you can't add different powers. Even if it was something as simple as y squared plus y cubed without the x's there, there's no way in general to add those two together. That's as simple as it gets. So let's move on here. What if we're multiplying these same terms together instead of trying to add them? What if we had y squared x cubed times y cubed x squared? Yes, we can simplify this. So we want to take, since everything's multiplied together, we can group the y's. And what's the rule when you're taking y squared times y cubed? How do you group those together? The rule is to add exponents. Now, why is that? Let's just think about that real quickly. Before we do anything more complicated, let's look here. X squared times x to the sixth. We add exponents because what x squared means is x times x. And what x to the sixth power means is x times x times x times x times x times x. And so we add those exponents because here in green we have 2 x's And here we have 6 x's, and altogether that's 8 x's. 2 plus the 6 equals the 8. So we end up with 8 x's all multiplied times each other. So when you multiply, add the exponents. And so it's the same thing over here in this slightly more complicated version. When we've got x's and y's, we just combine the y's and we get y to the 5th, 2 plus 3, and we get also x to the 5th. All right, well, let's look at the next one here. What if instead of having whole numbers as exponents, what if we have something else? 0.8 and 0.1. Can we simplify this, and if so, how? Yes, we can. And it's the same rule. So add the exponents. So we take x to the 0.8, x to the 0.1, and this equals x to the 0.9. Just add 0.8 plus 0.1. Now let's just take a minute to discuss what does an exponent mean when it's a decimal like this. Well, what x to the 0.8 power means is to take x, raise it to the 8th power, but then do the 10th root. So what we would be asking here, x to the 0.8, is trying to find what number x, if we raise it to the 8th power, multiply it times itself 8 times, but then the 10th root asks what number do we multiply times itself 10 times to get that number. So, for example, the 10th root of 100 would ask, what number can I multiply times itself 10 times and get the answer 100? All right, so add the exponents. So what about here? What if we have a ratio of two variables that have exponents, like x to the 7th divided by x cubed? You subtract the exponents. Well, why is that? Well, I always want us to think, not just memorize what the rule is, but why is that the rule? Well, on the top here, we've got x times x times x times x times x times x, so 7 x's, right? And then on the bottom, we've got x cubed, that's 3 x's. And so we subtract the exponents. When we're done, we're going to be left with x to the 4th, because you can think about canceling those 3 x's with those 3 x's, and we're left with x to the 4th, x times x times x times x. All right, what's the rule going to be if we have these decimal exponents or some kind of fractional exponents? It's exactly the same rule. Subtract the exponents. So here we're going to have 0.8 minus 0.1 equals 0.7, x to the 0.7. And we're going to be dealing with fractional exponents a lot in this class. That's why we're practicing with them a lot today. All right, what about this one? Here we have x squared raised to the 4th power. What's the rule? The rule is multiply the exponent. Now let's think about why that's the rule really quickly. Well, why that's the rule is because, well, x squared is x times x, but then we're raising that to the 4th power. So that means we have x times 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 x, right? 4 times. X squared times itself 4 times. And so we end up with x to the 8th. So that's why we multiply the 2 times the 4 to get the exponent x to the 8th here. What about x squared to the 1/2? What are we going to end up with there? Well, we multiply those exponents, of course. And so 2 times 1/2, so 2 times 1/2 equals 1. And so what we get here is just x to the 1st power. Now, this is a very important general rule that we have to know. And the general rule that I want you to think about here is anytime you have x raised to any exponent, let's just call it k, x to the k, whatever it is. Doesn't matter if it's a whole number exponent, a fractional exponent, or whatever, if you have x to the k and you want to get rid of that exponent k, the way to do it is to raise to the 1 over k. Raise that whole thing, x to the k, to the inverse. Because whenever you simplify that, you're going to have k times 1 over k, and that's always going to equal 1. So it's a simplification rule that's very important to always be thinking about. All right, let's think about simplifying fractions. How do you divide a fraction by a fraction? Well, if we had 1/3 divided by 7/8, you can multiply by the reciprocal, or multiply by the inverse of 7/8, right? So divide a fraction by a fraction is the same as multiplying by 8/7. And then how do you multiply a fraction by a fraction? You just multiply across. So 1 times 8 is 8, and 3 times 7 is 21. So 1/3 divided by 7/8 is the same as 1/3 times 8/7. It's 8 over 21, 8/21. And again, if we were really using this in a problem, we might want to represent this as a decimal number, 8/21, right? How about if we had something like 3 times x to the 0.8 times 0.5x to the 0.1? What we want to do to simplify this is take the constants here, 3 times 0.5, and group those. 3 times 0.5 is 1.5. And then deal with the x's. So we have x to the 0.8 and x to the 0.1. That's x to the 0.9, right? So x to the 0.9. All right, well, what if we had something like this? Now, when I'm dealing with exponents and fractions, I like to line them up where they're on top of each other. It just makes it a little clearer what we're doing. So y cubed x squared. And then I can see the y's in a column, and I can see we're going to take the 2 minus 3. So 2 minus 3 is going to leave us with y to the minus 1 power. All right, so we're going to leave y to the minus 1 power times x cubed and x squared. 3 minus 2 is 1, so we're going to have x to the first power, which we don't have to write the first power, but we know it's to the first power if there's not an exponent there. Or another way, and I don't like negative exponents personally, but for you, if they're fine, don't worry about making me happy. You make me happy by doing things right. Write things down in a way that you're comfortable with, and I will get it, all right? So I would prefer personally to look at x divided by y, because y to the minus 1 power is the same as y in the denominator. Either way here is perfectly fine. All right, here we have some fractional exponents. So how are we going to simplify all this? Of course, we're going to add those exponents. So y to the 0.2 and y to the 0.3 is y to the 0.5. And x to the 0.3 and x to the 0.2 is x to the 0.5. Another way we could write this is if maybe you like 1/2. 0.5 is the same as 1/2, so we could write it this way, and it doesn't matter which order we put the x and the y in, but we could say x to the 1/2 and y to the 1/2. Or we could just say, well, I know that the 0.5 power is the same as the square root, so we could write it as the square root of x times the square root of y. Or just the square root of x times y, all under the same little root symbol. All these are perfectly fine ways to write this. And I don't care which way you prefer, all right? As long as you're okay with it, and as long as what you're doing is correct, I'm happy. All right, now here we have a fraction with fractional exponents divided by another fraction with fractional exponents. So what are we going to do here? Invert and multiply. So y to the 0.2 divided by x to the 0.7 times the inverse of this. So we have y to the 0.8 and we have x to the 0.3 What's that going to simplify down to? What's 0.2 plus 0.8? It's 1. So here we have y to the first power. And in the bottom, we have 0.7 plus 0.3. We have x to the first power in the denominator. So that's just y over x. Although you could write that as y times x to the minus 1 power if you preferred. All right. So let's practice dealing with some of these exponents on a calculator. So you're going to want to find on your calculator a key that is like y to the x or x to some power. Sometimes it's x to the y to the x power on different calculators. So suppose we knew that p to the 0.5 equals 4. What is p going to equal? So here we want to practice this rule we were talking about above, where no matter what power you have, to get rid of it, you want to raise both sides to the inverse of that power. So what we want to do here is raise both sides of this equation to the 1 over 0.5. 1 over 0.5 is 2. So we want to square both sides. So p to the 0.5 to the 2 power is just p. And 4 squared is 16. This is a general principle. So here we have x to the 10th power equals 10. What's x equal? Now, if you just jumped in without really thinking and you said something like, well, x is 1, no, that's not right. And I want you to think about why that's not right. If you say that 1 to the 10th power equals 10, of course that's not right. What's 1 to the 10th power? Right, 1 to any power is 1. 0 to any power is 0. So we want to do this carefully by thinking it through and using our calculator. So the rule is to get rid of the 10th power, raise both sides to the 1/10th power. So here 10 times 1/10 is x to the first power on the left. And then we have to do this on our calculator. There's no other way. So 10 raised to the 1 divided by 10 power, or 0.1 power, however you want to think about it. And we get a number like 1.259 approximately. How many decimal places should you use? As many as you can. I'd say use at least 3 or 4 significant digits, especially if that answer is going to be used again. But as we go through the class, we'll kind of get a feel for what I think the minimum rounding is in various situations. If you're ever in doubt, whenever I do my answers, I usually leave the entire answer in the calculator if I need to use a number again. But as we do problems, if you round something a little differently than I do, that's fine. It's just in the next step of the problem, your answer is going to be a little different than what I get. And we have to get used to that in this class. All right, here L to the 1/3 power equals 2. So go through the process. How do we get rid of an L to the 1/3 power? Raise both sides to the 1 over 3 power. Raise both sides to the 3 over 1 power, right? Which is just 3. And so we have to raise 2 to the 3 over 1 power. And 2 cubed. L is 8. Here we have q to the 0.21 power. It's the same rule every single time. Raise both sides to the 1 over 0.21 power. Whatever that is. Raise both sides to the 1 over 0.21. And just do that on your calculator. So on my calculator, I'm doing 5 raised to the, and then in parentheses, 1 divided by 0.21. And you should get something about 2,130.24. 2,130.24. 0.24. And our last problem in this little section is just adding an extra step. A lot of the problems we do are going to have many intermediate steps before you're done. And I just want to get us used to thinking about that. It's almost never going to be one little simple problem and then we call it quits. We're usually going to have many steps and then we're going to want to interpret what we've done as well. So just to give us practice here, I say suppose n equals 4, and then we have this equation with two variables. What we're going to want to do is plug in 4 here for n, so we have 4 to the 0.7 times p to the 0.3 equals 10, and then we're going to want to solve that for p. So we're going to have a few steps to go through here. Figure out what 4 to the 0.7 equals. About 2.639. And then we're going to want to divide both sides by that 2.639. But again, there are different orders you could choose to do these things in if you like. So 10 divided by 2.639, what do you get? Well, we got p to the 0.3 on the left equals about 3.789 on the right. And how are we going to get rid of that 0.3 power? Raise both sides to the 1 over 0.3 power. So raise that to the 1 divided by 0.3, which I think is 3.3333333. And we get that P is somewhere in the neighborhood of 84.827 or so. And again, if your answer is a little off from what mine is, okay, but make sure you're close and that you know approximately where you're rounding. Gave you a little bit different answer from what I got.